So with that winded introduction in mind, thanks for having me. I'm Daniel Genkin. I'm an assistant professor at CSE, Go Blue. I work on side channels, which is a fancy way of saying breaking processors. And today we're going to talk about how hardware fails and what can we do about it. So before we start talking about hardware failure, though, let me walk you through the software development. Let me walk you through the software development lifecycle. So we typically start with an idea, nice and crisp and blue, and lives there on the sky, white as snow, pure, awesome, and amazing, and everybody wants to implement it. The problem is that, well, ideas, they don't live up there in the cloud. Instead, well, there is reality. In reality, there is hardware. And then somebody has to bridge the gap between this reality and the hardware that this idea needs to run. And we call them implementers or angels. And those angels are tasked with taking great ideas and bringing them all the way down to hardware. We can all use them and play around with them. Unfortunately, sometimes angels get it the wrong way. And when they get it the wrong way, they end up in a place which I call implementation hell. And why is it implementation hell? Because there are plenty of members in the community which would happily pounce on you and explain to you the errors of your ways and how did it all go wrong for your implementation in a form of wonderful papers producing PDFs with your name on it. And you can basically see this talk in a way on how to avoid implementation hell, how to not have this happen to you. So with this somewhat gruesome outlook, let me start with an idea, one of my own ideas, which is nice, pure, and snow, and let's see how many of you would like to implement it. So I've identified a major problem in today's economy. We are underutilizing juicers. We all have this device in our home, and we use it to make juice. Now, the problem is that, well, we became house conscious, and breakfast used to be this thing of ice cream and Cheetos, but now we make house conscious things. So we went on Black Friday, we bought a juicer, we stuck it on our kitchen, and that juicer, we make it to make juice. How do we do it? Well, we wake up in the morning, we are health conscious, so we let go of the Doritos and ice cream, and we make 1 cup of juice. And after we made 1 cup of juice, we go to work. Well, pre-COVID, go to work meant taking your stuff and going out of your house. These days, go to work means go sit in your living room and talk over Zoom. Okay, fine. So we sit down, over Zoom, and we run our working day. Then we have lunch break. Again, used to be get out of your office and go scavenge for food. These days, our kitchens are very close to offices, so we go to our kitchen and we make another cup of juice. Then we work our afternoon shift. We go home. What does go home mean? Well, we step out of our living room into our kitchen, make another cup of juice, and go into our bedroom to watch TV. So overall, about 4 cups of juice a day if you're very health conscious, and for that you need to own your own juicer. So how about we fix that? How about we make a public juicer, a juicer on the cloud, which everybody can utilize? We'll have a cluster of juicers, and we'll use all of them to make juice. How? By simply everybody can submit their juice requests in parallel, and then with a drone, you're going to have your juice delivered to you. One thing we absolutely must require is that if we have this public infrastructure of juices which would allow everybody to make juice on the big juicer up there in the cloud, is that, well, if 2 people make 2 simultaneous requests for 2 different types of juice, then we must require that 2 different types of juice come out, because frankly, I hate tomato juice. And it gets worse than that because, well, if you have a public infrastructure, then some folks are more creative than others in submitting their inputs. So assuming that this is made out of chocolate and not the other thing, then we expect this to come out. Okay, by a show of hands, who thinks it's a good idea? Who wants to quit their daytime job and go work on building this and joining my startup that are going to make a public cloud of juicers? Who thinks it's a good way? Anybody?
I don't know. Usually there's one person who wants it.
Anybody thinks this is a good idea? Okay, now Jamba Juice, where it is. Well, yeah, but Jamba Juice doesn't let you submit juice requests for free. There is a menu and authentication in the form of your credit card, right? You can't just submit anything you want. And they don't try making two juices at the same time using the same juicer. Okay, so I think we can all agree that this is a bad idea. But if we all agree that this is a bad idea for juicers, why are we making computers do just that? And the short answer is economics. Well, computers are more expensive than juicers, and therefore it makes economic sense to do that for computers, but not for juicers. Juicers are cheap enough for each of us to have their own. But if we were to recognize and to be honest with ourselves that this is what we're doing, and we're doing it to economic pressure, we also must compromise on the product we'll get. And in particular, when it comes to hardware security, sharing is not caring. Sharing is an expression of hate. Something would always be visible, something will always leak, and if we are to do this, we need to redefine acceptable notion of leakage, and it means that we have to balance leakage with performance, and historically we're not very good at that, because historically we've focused mostly on performance and very little on security. So let me show you the first example of what a hardware side channel is. So this is what's known as a prime and probe. We have a very fast execution core right here. We have a sorry, touch screen is not being cooperative. Give me a minute. Yeah. Okay, we have a fast execution core, and we have a cache to hide the memory latency of the fast execution core from the slow memory. Okay. The cache is a small piece of memory made with a different technology that makes it much, much faster, but also much more expensive and therefore much, much slower. And turns out that as soon as you have this caching architecture, you immediately allocate yourself. You immediately expose yourself to a security problem. And that's what's known as a cache attack. So let me run you through a cache attack very quickly. I have my attacker, I have my victim, and the attack starts by having the attacker allocate a memory buffer that is of size of the whole cache. And as the whole cache is being populated, basically the whole as he accesses his buffer, he's populating the entire cache with his own data. And then we wait. And as we wait, the victim runs. And a while after as the victim runs, it needs to touch memory. Problem of victim touching memory in this situation is that the cache is frankly full of crap. It's full of the adversary's crap. So something needs to go out. And then when the victim finished running, so the orange piece of data got cached following the victim's run, then we start the attack phase. Execution returns to our attacker, and the attacker starts accessing its memory while measuring the latency. First two memory cells come back super quick. But the third memory cell, well, it comes back slow. Why slow? Because it got evicted due to activity of the victim. Which means that as soon as you see slow memory accesses, you know that the victim touched something. And not only that, you know, because of the structure of the cache, if you know the address your address that got evicted, you can deduce which address was accessed by the victim. Okay. So basically, you can learn memory access patterns by other people's processes. It's not the data itself, it's just the access pattern. Who accessed which address when? Okay. Everybody good with this? Does that make sense for everybody? Okay, cool. So let's see how bad this is. And I'm going to flip this around and I'm going to start talking about software. So forget about hardware for a minute. Let's start talking about software. And more specifically, let's talk about RSA. RSA is that a crypto system, you don't really need to know all the facts, except that the secret key is an integer D. And in order to decrypt RSA, you need to compute C to the D mod n. Well, how do you actually compute C to the D mod n? Well, that's a good question. You can't do it in hardware. These numbers are too large. These are 2048-bit numbers. You just can't do it. So in hardware in one go, you need to do it in software. How do we do it in software? Well, here's the modular exponentiation algorithm in all its glory. 5 lines of code, but 5 lines of code is usually too much to go over Zoom in a webinar format. So instead, what you really need to know is that we have one loop here. You go over the bits, the key bits 1 bit at a time. And if the current bit is 1, you do a multiplication. If the current bit is 0, you don't. Everybody good with this algorithm? Yes, no, maybe, maybe not. I need to see some love from folks. Okay, good. So that's what's known in the technical language of side channel attacks as an oy vey incident. Why oy vey? Oy vey is the Jewish equivalent of oh boy. Why oy vey? Because we have secret dependent access patterns. How do they look? Well, if the secret bit is 1, go and do this ugly multiplication operation. And if the secret bit is 0, don't. And let's say I'm going to start probing the addresses, the code addresses of the squaring function and of the multiplication function. And I'm going to measure the latency it takes to access these 2 addresses. How does it look like? Like that. Okay. Every time the latency drops, so red means memory. Sorry, red means square. Every time the latency drops for the squaring address, well, why is that? Because you're doing a squaring operation. And then if you're doing a squaring operation immediately after that, well, then the key bit is 0. And if you're doing a squaring operation followed by multiplication operation, then the key bit is 1. And you can read out the entire key like that. Okay? And that's how ugly it is. Everybody good with this one? Okay, cool. So that's what's known as the war in caches, or the cache side channels. Memory operations take different amounts of time to complete because of caches. It's a basic design flaw in every modern CPU. It's there. Every CPU has this. Tough love. If you are using crypto libraries, you must use constant time coding. And it basically means you're not allowed to have data-dependent control flow. Let's think clearly about what I just said. You cannot have data-dependent memory accesses. You cannot have data-dependent ifs. You cannot have data-dependent lookups. You cannot have data-dependent loops. Good luck programming this way. Luckily, I don't need to program like this because I just break this stuff. But all of you that do try to build stuff, I'm sorry, I have no good news for you. There is one person who I know that can program like this, Daniel J. Bernstein, also known as Master Yoda. The rest of you considered having your programming license revoked because you don't know how to do this. Okay, I don't know how to program in constant time code either. There has been a tremendous effort by the cryptographic community to basically rewrite all of cryptographic code to be of constant time. A lot of this was done by DJB, Daniel J. Bernstein. But what about everybody else? Your TLS server, your neural nets, your image rendering hardware, your private chat applications, and let's not forget the blockchain. Everybody needs constant time, and nobody has it. And if you don't have constant time, then somebody would measure latency. Okay. And that's the caching war. Questions about this? Yes, no, maybe, maybe not. Everybody good?
Yeah, looks like we're good.
Okay, cool. So, and if you think that this is bad, This was the state of the art from circa 2006 until 2017. We were all worried about leaking addresses. And then 2018 hit, and these three guys joined our lives: Meltdown, Spectre, and Foreshadow. And then basically it all went to hell. If you think that this is bad, you ain't seen nothing yet. This is how it's going to escalate very quickly and become much, much uglier. So let's talk about Meltdown. We have a CPU, and it's a shared system among many security domains. What do I mean by that? Well, the CPU has an L1, L2 cache, L1 cache, an execution core. And on top of that, we are running an operating system. OpenSSL holds some keys. We have VMware running some VMs, and you use your data in the form of happy cat pictures. And of course, we also have our adversary. Now, it's the CPU, it's the execution core's responsibility to prevent applications from crossing security domains. Now, it's a very big sentence that has a lot of technical words in it. So let me demonstrate what do I mean by that. So we have an adversary, a user-level program. And let's say it tries to access the operating system. What's going to happen? Well, the execution core is going to detect that, do a permission check, realize it's a user-level program trying to access kernel data, and basically issue a stop, issue a fault, go into an interrupt, return control to the operating system, to the interrupt handler, and the operating system is going to realize that this is not an application that is allowed to run anymore and crash it. Okay, and that's what's called as a segmentation fault. On the technical level, how is this implemented? Well, there is a mechanism inside the processor, a hardware mechanism that checks permissions. And if the permission doesn't satisfy, well, it raises an exception, returns control to something that it knows is the operating system, and the operating system crashes the offending article. Okay, from a technical perspective, the instruction that is trying to cause something, that is causing something that it's not allowed to do, is called a faulty instruction. It caused a fault inside the core that caused the diversion of control flow somewhere else. So what's the main discovery behind Meltdown? Well, it's that before the crash comes, actually the attacker gets the data. What do I mean by that? I mean that if you have an execution core, we have an malicious, an adversarial process trying to access the operating system, well, this program will crash somewhere in the future. In the meanwhile, before it crashes, what's going to happen is that the core is going to speculate forward, and assuming that the data is cached, first thing that happens before the crash is that the adversary gets a copy. Remarkably, there is even enough time to leak it via a cache side channel until eventually the permission check catches up and kills the offending program. Of course, by then, too little, too late. And if you want to see how bad this is, you can dump the kernel in 3 lines of code. And it's not only about the kernel, it's also about virtual machines, SGX, and pretty much any other security domain you have on your computer, because you can abuse a trick from a page table walker to generalize Meltdown to pretty much anything in your physical memory with 1 little line of code that makes everything worse. So that's Meltdown. And as I said, Meltdown is really in 3 lines of code. So let me show you how it's done so that you won't be angry at me and believe what I told. So let's say I have a pointer, and this pointer points to some kernel space, and there is some secret in this kernel space. And for the sake of this example, secret equals 3. And I have my nasty code that does Meltdown. So let's see how this code runs. So we take pointer, and before dereferencing it, we read it. Reading the pointer is okay. Dereferencing it is not cool, but reading it is okay. And then the pointer is being brought from the virtual memory into the cache and into our attacker monster. Then what do? Well, we promptly dereference it. Okay, let's dereference it. This program should crash, but for now, first thing that happens, is that adversary gets a copy of our data. We take 3, we multiply by 256, we get 768, and then array 2 of 768 is being brought to the cache and into our attack. Eventually, of course, at some point, the processor is going to catch up. And when the processor is going to catch up, well, it's going to raise an exception, kill the offending program, tear down its address space, and restore sanity. Right? We're done here, right? There's nothing more to see. Anybody sees the problem here? Why is this super not cool? Why is sanity has not been restored? Why is this not yet another program that crashed and burned? What's wrong? The cache wasn't cleared. Matthew, you're close. Want to try being more specific? Side channel leakage. Anybody sees this? Can somebody name the color of the leakage in the cache? The 3 options: yellow, red, or purple. Where do you think the leakage is? Red. No, it's not red. Red you cannot access anymore. Purple. This. What is this doing in the cache? Who touched that? Whose cache line is this anyway? Well, this got cached because of incorrect execution of the green monster that is now dead. But that green monster had its access patterns highly depend on the secret that it should not have gotten. So we have a piece of memory that is cached because of something that should not have happened. So let's exploit it. I bring up a red monster. And my red monster goes like, let's measure the latency of array 2 of 256. Well, nobody ever touched array 2 of 256. So it's going to take a long time to leak. So it's 256 is not the right answer. Let's measure the latency of 512. It's going to take a long time also. So 512 is not the right answer. As soon as I touch array 2 of 768, the result comes back super quick because array 2 of 768 is 256 multiplied by 3. And I can deduce the data equals 3. That's meltdown. That's how you read a kernel byte within 3 lines of code. Questions about this? Everybody good? Okay, purple not yet. There are questions. I can't see who asked it. So can somebody, your name is anonymous. Can you type in the question? Okay, so let's see this live. Let's see how bad this is. I have a password manager right here. And as I'm going to type in the password, I'm going to start my kernel probe. And as I type in the password, it comes out on the on my terminal. This is really bad. Okay, the leakage is hundreds of kilobytes per second. It's on every Intel processor ever made prior to 2018. It's in hardware. We cannot fix that. And it basically breaks every possible security domain you have left. Because if the user can read the kernel, the user can do bad things. For example, recover passwords. So what do? Well, when in trouble, when in doubt, run in circles, scream and shout, which basically means panic. Wide scale panic. My personal favorite headline here is kernel panic. Okay, it is literally panic. There is little we can do. Okay. So what do we do? Okay. First of all, after you unleash this evilness, well, if you unleash this evilness to the universe sends you an email asking you, why did you do that for? But then we start building new hardware. What new hardware? Well, the 9th generation desktop processors, also known as Coffee Lake Refresh. So, what was the state of the art after Meltdown? We had old CPUs that are Meltdown vulnerable. The problem is in hardware, but because hardware is hard and you cannot fix hardware, we mitigated it in software. It's called KPTI, kernel page table isolation. There is also a bunch of other mitigations for foreshadow, the generalization. And well, it's 30% slower. Sorry, it's 30%. It causes machines to be 30% slower. Okay. If you're using a computer that is made pre-2018, that is meltdown vulnerable, sorry, pre-2019, that is meltdown vulnerable, your machine is 30% slower for what it could be, and this is my gift. This is the gift from me to you. You're welcome. I know you always wanted slow machines. Well, now you have them. Okay. There is no choice here. We used a different permission check that makes that is serial and not speculative. Problem is, it's a software permission check as opposed to hardware one, so performance drop is what you get. But we also got new hardware launched by Intel that were supposed to be meltdown resistant. What did they do? Well, this is the 9th gen. These are the 9th gen cores. I'm going to denote it as the core i9, but there are other cores there in that architecture. These are fast countermeasures because they've re-implemented the permission checks. So we can now disable the slow software mitigations. What do these fast hardware mitigations do? Don't ask hard questions. We don't really know. It's interproprietary, but well, trust us, it's going to be fine, right? So that was 2019. Any questions about Meltdown before I start talking about these amazing hardware countermeasures and why they're all broken? Any questions about Meltdown? Okay, cool. So, as 2019, what was the microcode update that had this mitigation? Was there a microcode update? Yes, there was, and it bricked a bunch of computers, because when you're trying to push microcode for every computer out there made by Intel, then the outcome is that some computers won't boot back up. So like Intel accidentally bricked half of percent of all the computers out there. But yes, there was a microcode update. Everything I'm going to talk about pretty much had a microcode update, and some of them gone really, really bad. Matthew, did that answer that? Cool. So let's talk about MDF. So as 2019 went down to a close, two things happened. First of all, I joined Michigan, which means that I need to do research and build a hardware security group and do some damage. And the other one is that I didn't really believe that, well, whatever thing that Intel tried selling us is of any good. So we started looking what else is in the processor. And here's what we found. There are more things in the processor beside the cache. There are buffers. The fill buffer, the store buffer, the load port. These are internal data structures that sit between the execution core and the caches. Well, what do we know about these buffers? Nothing. They are proprietary, made by Intel. How do you learn about buffers without Intel publishing the designs? Well, you read patents. Lots and lots and lots and lots and lots of patents. Okay. By the way, reading patents is a good way if you have sleeping problems. I highly recommend, if you have sleeping issues, start reading patents, because, well, it's the best night's sleep I ever had. Okay. But the nice thing about patents is that if you read them, then you get nice nuggets. Now, patent language is, well, a bit hard to read sometimes. So I'm going to go over it slowly and multiple times with you, and let's see what we learn out of it. If there is a hit on the store buffer and the physical address of the load operation is not valid, the physical address check may be considered as a hit, resulting in value forwarding. Okay, that was too much English. So let me try doing it again, a bit, this time more technical. If there is a hit on the store buffer, okay, so there is some piece of data that is in the store buffer. So there is a store buffer, new thing learned. It has some data in it. And the physical address of the load operation is not valid. Okay, so we have a load operation in flight accessing to an invalid address. The physical address check may be considered as a hit, which means stop checking addresses, you don't care anymore, resulting in value forwarding. Let me summarize this in one sentence. If you have a crazy load trying to access data that he is not allowed to access, forget about checking physical addresses and just give it some data out of the store buffer. Basically, the CPU serves wrong values deliberately to faulty loads. Why? The load is faulty anyway. This program will crash somewhere down the line. There is no point in checking anything further. Just give it something, because it needs an answer now. It's going to crash anyway. Okay. From a security perspective, faulting loads give away other people's data. You want to see the code for this? Take a null pointer, dereference it. First time I wrote this code, my mind broke. What do you mean you take a null pointer and you dereference it? Well, that's what you do. And then you also expect to get an answer out of it, which you then put in a variable called secret that you then compute over by doing a memory access. Somehow, they never taught me to write this code. I've never seen this code pattern before. And my mind bricked first time I wrote it. Okay, I literally had to walk away from the keyboard for a minute or two to recover. But guess what? Here's what happens. As the execution core is trying to store a value in memory, I sit there as an adversary, issue a faulty load, get a copy, and leak it over the cache channel. Which means that an attacker can sit there and siphon off data belonging to others, despite all mitigations. You have a CPU full of data, issue a faulty load, and get a copy of anything on those buffers. That's MDS. Questions about this? Everybody good? Yes, no, maybe, maybe not. Everybody happy? And Matthew, I see your X470 nightmare. Yes, I haven't taken X470. I didn't come from Michigan, but this is my architecture nightmare. I agree with you totally. Yes, Adam, Intel isn't happy. Everybody good with this one? So, how do we fix MDS? Well, we have a buffer that is leaky. Ideally, you want to check permissions before giving data from the buffer. But we can't do that. We can't do that for two reasons. One, there is no time. The buffers need to respond faster than the permission check. And two, it's in hardware, and we already shipped the hardware. So we can't modify the hardware after we shipped it, right? So, well, sorry, out of luck. Well, the approach taken by Intel is that, well, if you can't beat them, flush them. They modified an old legacy instruction called VERW that basically flushes buffers every time you call it. And you're supposed to execute VERW every time you change a security domain inside your core. You're supposed to flush the buffers. Okay. And now the adversary can sit there, issue faulty loads from here to tomorrow. Nothing is coming out, because, well, the buffers were clean. Okay, so that's the mitigation for MDS. But I don't know, something still felt bad. Why did it feel bad? Because, well, it's an engineering clutch. And here's some hard questions about this clutch. Is flushing the same as not leaking? Is flushing even sufficient? Is this the right answer here? Because, well, we couldn't fix it. We couldn't implement a permission check. So instead we did some clutch, but well, clutches, when it comes to hardware security, it's dangerous territory. Now, from the other side, from the adversary side, MDS left me a bit unsatisfied. Because MDS is like drinking from a fire hose. You have a lot of data. There is no limit on what data you're going to get because there is absolutely no others check. But it also means you don't know whose data you're going to get. You're going to get some bits. It's up to you to figure out how does this data relate to the data you got previously and how will it relate to the data you get tomorrow. It's completely not clear how to sift through all this data from the noise. And the main challenge when it comes to MDS is actually sift all the noise you're getting from the data you want. Now, ideally, I don't want to be like this girl. I want to be like this cat, in full control over the leakage, taking in every little single drop. And that's one thing that left me kind of unsatisfied after MDS. The other one is, how do we fuzz CPUs? How do we test CPUs for leakage? And I use the Intel Inside logo. This is the logo from Intel Labs, experience what's inside. How do we experience what's inside? Before what's inside comes experience us in the form of performance slowdowns. So that was my 2019. And as 2019 started dwindling down to the close, we started figuring out how do we test processors for leakage. And very quickly, we ran into something that would lead us to a paper called Cashout, which we call Project Unflush, because the main question here is, how do you unflush whatever just got flushed down the drain? Okay, or put it the other way, how do you clog a toilet? Okay, so what's the main observation behind MDS? First of all, that it only, the main observation behind VW. First of all, it doesn't fix the problem. It merely cleans out the buffers. And when we started running our unit tests, we empirically observed 0.1 bytes per second of leakage, despite VW mitigations. So let me tell you what this means. 0.1 bytes per second of leakage means 1 byte per 10 seconds. In computer time, it's eternity. It basically means that there is some data that was statistically significant, but it's not clear what are we leaking. Okay, we literally had no idea, besides the fact that statistically it's there. We were sitting there issuing faulty loads, use dereferencing a null pointer, and getting a copy of what? I didn't know what. We had no idea. But it was there. First thing you do, you go, oy vey. Again, an oy vey moment. Second thing you do, you call Portland. Portland, you have a problem. Why Portland? Because that's where Intel hardware security is. So we called them with this and we went like, guys, it leaks. Here's the unit test. We don't know what we're leaking, but it leaks. Came back, yeah, there is no such thing. There is no leakage here. I'm like, did you run the program for more than 10 seconds? Came back again, yeah, there is nothing there. I'm like, okay, did you run the program for more than 2 minutes? Yeah, we're seeing something, but there is nothing there. We don't know whose data is it, so it's noise. And in my group, there is a saying, there is no such thing as noise on the processor. There is only other people's data. Why? Because it turns out that there is another bus on the processor. It's the bus responsible for draining the L1D cache. And it actually makes perfect sense because, well, the L1D cache is a finite object, and when it overflows, it needs to go to somewhere, to the L2. And you would expect this bus to look like this orange line. But actually, it doesn't look like this. In some corner cases, Intel uses the field buffer as a way to drain the L1D. And this is weird because the field buffer, as its name suggests, is on the intake side of the hierarchy. Why are we using the pipe used to fill the pool in a way that we are reusing it to drain the pool? It's already weird, but they did. And the field buffer is also on very, very, very shaky grounds because we know it leaks from MDS. And making things worse, Intel was completely unaware to the fact that it behaves like this, that there is a way to drain data through the field buffer. And all of this combined means that MDS is a much, much, much bigger problem than we ever thought. This little arrow here on the eviction side of the L1D completely changes the picture when it comes to MDS. So let me show you Cashout. But before showing you Cashout, let's recap MDS, because probably half of you forgot what it means. So MDS targets data in flight. What does data in flight means? It means that as the execution core is trying to access memory, it's being brought into the hierarchy, and if the adversary were to execute a faulty load, you get a copy on the bus. Anything being touched by this bus, you're allowed to have a copy. If somebody is reading values, you can issue faulty loads and get copies. Data that was not touched is out of bounds. If the data is not on the bus and it's statically somewhere, you cannot get it out. Okay, so that's MDS. But let's talk about Cashout now. Cashout targets data at rest. So let's see how this looks. Let's say I have a victim, and my victim is trying to touch some memory. Let's say the blue memory. So the blue memory is being populated into the hierarchy, and then L1D gets a copy, and then it's brought to the load port and to the execution core, eventually consumed by the victim. And look, no adversary. Nobody came. Nobody issued faulty loads. And then some time passes. Still nothing. And then the operating system shows up and tries flushing the buffers because MDS, right? So we need to clean the buffers after use. Still nothing. And then some more time passes because I'm trying to store for time in case you didn't notice. And still nothing. Eventually, the adversary shows up, fashionably late to the party. And as the adversary fashionably shows up late to the party, he goes like, where is the data? Well, it's not in the field buffers, it's not in the load port, it's not in the store buffer. The L1D cache is secure. What do we do now? Okay, where is the data? Well, the data is in the L1D cache, which is the place where it's supposed to be secure following the Meltdown redesign. Okay, so let's rob the L1D cache. What's in the L1D cache? A lot of data, 32 kilobytes of data. Which data do we like to have? Eeny, meeny, miny, mo. Let's go for the blue. So first of all, we need to move it somehow. We need to move it from the secure cache into the field buffer. How do you do that? Well, remember, the cache is of finite size and is kind of small. So if I access data that needs to go into the same place as the blue data, then the blue data, well, is out of luck and needs to be evicted. So let's do just that. I'm the adversary, I'm gonna access my red data, and as I access it, the cache caches it and evicts the blue data. Good. Into the leaky buffer. Wonderful. Issue a faulty load, get a copy. And then you even have time to leak it over a cache side channel. Okay. That's Cashout. Questions about this procedure? About what Cashout just did? Everybody good? Yes, no, maybe, maybe not. Everybody good? I need to see some love from the chat or from the audience or for somebody. because I have zero feedback in front of me.
Yeah, no questions.
Okay, cool. So what is the outcome of Cashout? You saw that the leakage is 0.1 bytes per second? You wish. 2.85 kilobytes of data is all you get, is what you get. 4 orders of magnitude difference. Okay. And moreover, Cashout, if you think that MDS is the problem, Cashout is a much nastier version because now you get to pick what to leak and then leak it. Okay. Select what you want from the L1D cache, evict it, issue a faulty load, get a copy. You want the entire L1D cache? Sure, you can have that too. Just go over the sets one by one. You want 32 kilobytes of data out of somebody's address space? Yay, you can have it. The VW mitigation is completely useless as a defender, completely pointless, because, well, VW happens after the victim runs, well before the adversary starts the procedure of evicting something from the cache. And turns out that VW, I have a beef with VW. It's for the defenders, it's completely useless when Cashout came out. It just doesn't help. But for me as an attacker, oh, what a love story. Turns out that flashing the cache, flashing the buffers before starting the Cashout attack run improves the signal. Why? Think about it. When I dump stuff from the buffer, I don't have any control about what I'm going to get. I can choose what to evict into the buffer, but if there is something else in the buffer in addition to what I evicted into it, I don't know what I'm going to get. There is some probability I'm not going to get what I want. It would have been very helpful if I can remove unrelated data from the buffers before I start my attack run. So, and then there's going to be one thing in the buffer, the thing I just evicted, so I'll get that. If only I had an instruction that I can call from userland that would very quickly flash the buffers optimized in hardware. Oh, wait, I do. VW, that's what it's designed to do. Okay, and that's the minute where the cure is worse than the disease, because you can abuse VW to go from a leakage rate of 0.1 bytes per second to 2.85 kilobytes. 4 orders of magnitude improvement for the attacker, 0 help for the defender. Yay! That's how countermeasures should work, right? That's what countermeasures should do. They should help attackers making small problems big. Right? That's what countermeasures should do. Everybody agree on that? Everybody good? Yes, no, maybe, maybe not.
Yeah.
Cool. So, what can you do with Cashout? Well, let's say I have a user space program. I can leak AES and RSA keys out of somebody's address space. I can also leak neural network weights, because if you're sick and tired of cryptographic examples, then here's a machine learning example. You can also break ASLR and stack canaries out of the operating system. If you have a virtual machine, you can do all this cross VM. So here goes your virtual machine separation. And if you have a virtual machine, then you also have a hypervisor, then why not attack the hypervisor? And you can also break software guard extensions. This is, as a defender, this is how you know you lost. When the adversary is forced to stop because there's simply nothing left to take on the system. Okay, every security domain got broken. There are major microcode updates that came out after Cashout. All machines are slow again. All that was fast is broken. And that's basically where we stand today. I'm going to stop here because I'm kind of running out of time, and I think I have 10 minutes left for questions. So I'm going to skip to the last slide, which is I've recently started at Michigan only a few years ago, still looking for students interested in this stuff. If you like this sort of thing, come talk to me, because there's plenty left to break. And with that, I'll take your questions, folks. Thank you.
Yeah, thank you, Dr. Genkin. Not so much a question, but an attendee just wanted to thank you in the chat, in the Q&A chat.
Sure, thank you. Happy to entertain over the weekend.
And so I guess I have a question for you. How has Intel taken this? So when you've notified them about these issues, how have they taken it? Or have they been very responsive, or?
It's a love-hate relationship. Usually they respond after, because, like, you know, when they see the data leaking, then there is little you can say about it, right? Like, here it is. So it's gone better over the years, and its disclosure is always a tense time for everyone. So they're taking it as best as they can. Let's put it this way.
Yeah. And so Ernie was wondering, do other brand processors like Apple have similar problems?
Ooh. You're asking a tough question, one that I cannot talk about. But the fact that I cannot talk about it tells you that the answer is yes. Does that make sense?
Yeah, that makes a lot of sense. Of course, we have to be careful with disclosures. And Adam was wondering, how long did Intel leave that EPID key unrevoked?
Dude, don't ask questions that I cannot answer. A lot.
Yeah, that's too bad. Yeah, it doesn't look like we have any more questions.
M1 using x86 model. What do you think about Apple's M1 using x86 memory model for backwards compatibility? I'm not sure I understand the question, Michael.
It looks like he is wondering about your thoughts on Apple's M1 using the x86 memory model.
What does he mean by x86 memory model?
Matt, if you could clarify in the chat, that'd be great. He's typing it out now.
Okay.
So what got you into this area of security while we wait for him to type it?
I mean, I was doing cache side channels, and then we started thinking about speculation. And that's what came out, honestly. I'm part of the generation that started the original cache war, where you would measure other people's access patterns and like geek out about it and figure out how does it relate to the secret keys.
Gotcha. And what does your lab do for everyone in the audience, I guess?
Well, my lab, we do hardware security. We basically break this stuff. All of these projects that you've seen came out of my lab. That's what basically what we do. We break processors. Okay. We are the place where processors come to suffer. It says it on the door. They make, we break.
That's a great motto in security.
They make, we break.
And someone said in the okay, so Matt clarified, Apple's ARM M1 has a special x86 TSO layer for emulation purposes, and he was curious how well implemented it is.
Yes, I agree that it's a very good question. Honestly, I don't know. Why don't I know? Because I didn't have enough time to play with the Apple M1 with that specific thing, given all the other things we played around. It's a very good question. When it comes to hardware security, usually questions like this, the answer is I don't know, and go take a look. And that's exactly what it is. I don't know, go take a look. Might be very bad, might be very good, might be where the skeleton is buried. Nobody knows. I don't think Apple knows, because they don't know how to. No hardware vendor knows how to think speculatively yet, offensively at least. So nobody knows. It's a very good question, though. That's how these projects start. sorry if I can't say more, because that's all I know about it.
That's totally fine. Yeah, that looks like all the questions. Do you have any? Oh, looks like we have one more. Do you think Intel's x86 BISC circuits or Intel ME are going to introduce more
Of
attacks?
course, I got to introduce more attacks. Intel ME had already introduced a whole pile of vulnerabilities. Anytime you have things like that that are not in the line, not exposed to the light and cannot be reviewed, they're going to introduce vulnerabilities. That's just how this thing works. What do we do about it? I don't know. But yeah, every time you introduce something that complicated, that at such a lower place in the computing hierarchy, you're going to get problems.
Yeah, I guess we could expect to see something from you, from maybe.
Yep.
All right. Do you have any final thoughts or comments to leave us with? Or
No, I'm good. Thank you for having me.
yeah, thanks for coming out, Dr. Genkin.